explore some parallels between statistical physics and statistical learning and statistical machine learning. Then finally, I'm going to, before concluding, I'm going to set up the stage for quantum. So enter quantum, and I'm going to explore quantum hardware and a quantum algorithm or two, and try to motivate why the future of AI lies quite majorly in physics. So with that, let's begin. Now the broad definition for AI in most textbooks is defined as the study of intelligent agents that can study their environment, make predictions, and take actions to maximize their goals. Whereas physics, on the other hand, deals with observing nature, deriving an underlying mechanism to make future predictions. So at the heart of both the fields, there is an overlap because both of them make observations, build models to predict future events. But why talk about physics now? Because artificial intelligence, and in particular deep learning, has made incredible progress in a vast variety of problems like classifying images, self-driving cars, outperforming humans at ancient games like Go and chess, and even generating art and music. So surely progress in conventional deep learning methods and advances in computer hardware should be enough. Well, I'm going to argue that this is on the contrary. When I talk about artificial intelligence, I really am just referring to a subset, which is deep learning. And when I'm talking about deep learning, I'm basically talking about neural networks, which is one of the core deep learning methods. And neural networks were originally inspired by the brain's architecture. On the right here, you can see two different neural nets, a simple neural net and a deep neural net. Well, both of them have an input layer and an output layer where the data is fed into and read out. They have different numbers of hidden layers, which are in yellow. Simple neural nets have just one hidden layer, and deep neural nets have more than one. And that's the difference. And all the layers have computational units called neurons, where there's different sorts of functions that are being applied to the inputs to generate the outputs. Neurons across layers have connections of varying strengths called weights, and this again is to model the synapses in our brains. So if you go to a specific example, say supervised learning, where we have a neural network here, and it's being fed images of a panda or a chihuahua, and the neural network learns to match between correct input-output pairs. Basically, it learns to learn the function between image and label, input being the image and output being the correct label. And so how does learning occur? Well, the main algorithm behind the artificial intelligence revolution is backpropagation. And what we have here is a visualization of an error function surface. So if, say, we are shown an example of a panda and the network outputs dog, then we know that there's an error. So what the network does, it changes its weights to minimize that error so that it can generate the correct output. And these corrections in weight start from the output layer and it flows all the way back across the network. So in a way, it back propagates across the network. And we can see that just within a few iterations, the red arrow can reach the minimum, the value of the error function. And so we know that the network is doing a pretty good job at classifying images. That's all great, but real world problems are more complex. And these are some of the problems that are often ascribed with deep learning. Deep learning is often being dubbed as black box learning. We don't know how exactly the network comes at the conclusions it does. They're very slow learners. Algorithms require millions of training examples and consequently weeks of training very often. Not obvious how to incorporate prior knowledge. So for instance, if we are looking at the data set that exclusively has black and white pandas, then it is not obvious immediately how we can incorporate that knowledge into the neural network. The neural network has to kind of start from scratch and figure out what's a panda and what's a dog. And finally, as problems get more complex and human lives get involved, we need interpretable artificial intelligence. So how does physics come handy? Well, physics does not operate by going through lots and lots of examples. It operates by discovering symmetries. It provides an underlying mechanistic view, hence it is interpretable. And it's also easy to incorporate prior knowledge to update our models and equations. Now, I can argue that there are three core ingredients in deep learning models. Firstly, there's the structured data. So for our case, that would be images along with their correct labels. That is on what the network trains. Then there's the architecture. In our case, that would be a neural network with a certain number of hidden layers and certain connection probabilities between the different layers, how the different layers are connected. And finally, there's the learning algorithm, which could be backpropagation or stochastic gradient descent. And these three are very highly dependent because we need to pick out architectures and algorithms that can make sense of the data, that can learn with the data. If I'm drawing analogies between deep learning and physics, then a model in deep learning corresponds to a theoretical framework in physics. The algorithm corresponds to equations of motion, which govern how the different particles are behaving, and structured data corresponds to experimental findings. Now, as I said before, let's look at a neat example. An important hallmark in AI are what's called convolution neural networks. These are basically the go-to deep learning architecture and methods that you go for classifying images. It's designed by the architecture of our vision system. So that's obvious. And CNNs are extremely good at computer vision tasks like recognizing handwritten digits and object detection. In fact, CNNs outperform humans in recognizing handwritten digits, that is digits written by us. That's weird, but they are extremely good at these tasks. So how do they work? So here you can see a layout of a CNN. You have the image of a bird being fed into the network, and you have the architecture. So it proceeds by applying a convolution at every part, at pixel blocks of an image. And a convolution or a feature mask is basically a matrix. And we are performing a matrix multiplication on specific blocks of the image, and we are scanning across the image. That's what's happening. So if you look at the binary representation of the image, say it's just ones and zeros, the green matrix, then we're applying a yellow filter, which is again ones and zeros. And we're just carrying out the multiplication and scanning across, and that is generating a scalar, which is the convolve feature. So now the mask could be, say, the absence or presence of a edge. And we are basically getting the degree to which that edge is present in the image. And as we progress towards higher layers, we extract higher level features. So instead of an edge, maybe the presence of a loop or a figure of 8. And basically we reduce the figure of the bird into a stick figure image, and then we spit out probabilities that give us a sense what's the image of. However, now comes the twist. We make a very fundamental assumption that the images are all two-dimensional. They're very bad at dealing with three-dimensional images. But we know that we live in a 3D world. So to take CNNs out of this flat land, we require insights from physics. So here comes gauge equivalent CNNs. Well, one of our favorite terms in physicists toolbox is equivariance or covariance, which is basically the notion that physics and laws of nature is independent of the coordinate system, as Einstein put it very simply. And this is basically the center stage of Einstein's general theory of relativity, but that same thing finds use here. How is that? Well, first of all, like most of the three-dimensional images that we see are on arbitrary shapes, arbitrary manifolds. If we talk about shape of molecules or shape of proteins, or we are trying to diagnose tumors, then these are on very arbitrary manifolds. Well, there was some progress with what's called group equivariant CNNs that could detect rotated or reflected features of an image. So if there was an obvious symmetry in the image that we're trying to detect, say it's got spherical symmetry, then that's easy. But it's not good enough for arbitrary manifolds where there are no global symmetries to take advantage of. And the solution is gauge equivariance. The real problem can be very briefly explained with this picture over here. So imagine that there's a cylinder and there's a filter lying on the surface of the cylinder, and that's half black and half white. So it's detecting an edge. It's detecting the presence of an oval edge. So if we are moving around the filter around the cylinder and we're taking it to the top of the cylinder here, well, the orientation that we end up with depends on the path that we take. So essentially, we lose what's called translation equivariance. Like if I move something over to that side, the fact that it's the same, we can apply the same filter with the same orientation, that's lost. So what we do is that we place constraints so that neural nets only process gauge equivalent patterns across layers, so that CNNs can learn to recognize that these two images of the man these two poses are of the same object, and these have real consequences on prediction of cyclone data from 3D cyclone prediction from 3D climate data. It vastly outperforms what was state of the art before. And there is great potential for protein folding simulations and diagnosing tumors. All right, now I'm going to kind of change gears a bit and go back to physics basics and talk about two cornerstones: statistical mechanics and quantum mechanics. So firstly, just a very brief refresher on statistical mechanics. We just need two rules of the game. So one is that particles are driven to lower energy states. We minimize energy. And finally, we try to maximize entropy or disorder. So configurations that occur more frequently are more likely. So if you take an example of billiard balls, so before breaking the billiard balls, they are in a very neat configuration. And if the balls are sharing an attractive force, then it's in a lower energy state. But there's also lower entropy because it's a more ordered system. After the break, the balls get scattered, higher energy, but they are occupying a higher volume on the phase space, and consequently, there's more disorder in the system, higher entropy. And what's the dial between the two? That is temperature. Temperature defines the balance between the two configurations. And what we mean by this is that we are trying to actually minimize what's called the Gibbs free energy. Basically widespread everywhere in physics, biology, and chemistry. And minimizing Gibbs free energy, U minus Ts, translates into state probabilities that decay exponentially with the energy, and then there's a normalization with the partition function. And if we just take this state probability and discretize, then we arrive at Lagrangian dynamics, which is the rule for the update of states. So what we take away from this is that the states evolve towards lowering the energy, but then there's a noise term which scale as the square root of temperature. So now hold on to this equation, and we come to statistical machine learning, where we had stochastic gradient descent. This was the picture from before, where we had, within a few iterations, the network goes to the value of the loss function. So we are driven towards the value of the loss function, minimizing error. And if we combine what we had before, Langevin dynamics, then we can basically identify the energy term with the loss term, and we are trying to minimize both quantities, and we're just adding a noise term, which scales as the square root of lambda. Well, lambda here is the learning rate, the rate at which the network kind of rolls down the hill. And why this is great is because this opens up Bayesian deep learning. Before, we were basically rolling down to a singular point in this valley, but now there is a noise term. So what basically happens is that we get kicked around a bit, and instead of arriving at an optimal single value for the weights W in our network, we arrive at probability distributions for W, so that now we have error bars. We don't overfit to a specific training examples. And what's great is that we can detect unusual data. And this is because imagine that the network is classifying dogs and cats, and then it's shown a traffic signal. Now, a standard CNN is just going to pretend that there is nothing wrong. It's just going to find an optimal solution. And finding the optimal solution, it's going to predict that this is the image of a cat. But here, because of the noise term, we can detect unusual data. And so if you're drawing analogies between statistical physics and learning, state of particles correspond to parameters of weights, energy is identified with loss, and relaxing to equilibrium is the same as loss minimization. And there isn't an analogy with entropy yet, but hopefully we'll work something out. And that's it. Just taking an insight from a very basic law of statistical physics, we are already seeing that we are getting somewhere, which is exciting, and it opens up new capabilities for our deep learning networks. Now I'm going to turn towards quantum mechanics and kind of zoom out a bit. The success behind deep learning and AI has largely been due to faster computing resources, obviously along with the vast amounts of data that is being generated on the internet every day. So up to now, we are more or less having an increase in the computational efficiency more than twice every year. But to continue this progress, we need what it's called physics of AI. We need new physics-enabled devices because architectural innovations are not going to be enough. We need to enter the quantum domain. And to visualize this, with just GPUs, CMOS-based devices, and approximate, which is called mixed precision computing, we can get maybe a 10x speed up. With CMOS and analog, for instance, what's being proposed, neuromorphic computing, neuromorphic chips, we can maybe get up to 100x speed up. And to really step up the game, we need quantum computing. So that's going to be the next part of the talk. So there's different postulates that we have in quantum mechanics, but here we just need two of those postulates. We need quantum superposition, which basically states that the mathematical description of a particle is given by something called a wave function, and that's the superposition of different basis states. It's almost like adding up waves on a beach, but there's more involved mathematics involved. So we are actually dealing with complex numbers here. And what we do is that instead of just adding up different waves, we add up the waves with their amplitudes. And then we take the modulus square, the absolute value of that, to obtain the probabilities. And that's lead us to our next thing, quantum measurement, where basically expectation values of measurement operators is given by basically sandwiching the operator with the wave function. And basically the takeaway from this is that these two rules are enough to define quantum logic, and quantum logic already is richer than classical logic with several operators that do not have classical analogs. So I'm now going to give you an argument. So if you have classical bits, say a switch, a light switch, it can be in two states, one of two states, an on state 0 or an off state 1. But here you have what's called a quantum superposition of the two states. So that arrow, that vector, which is the state of the particle, is free to rotate in this sphere, which is called the Bloch sphere. And what you have consequently is that if you're now dealing with, say, two light switches, so both of them could be on, so 0, 0. Both of them could be off, 1, 1, and one on and one off, so 0, 1, and 1, 0. So we get four discrete states, and to represent these four states, we need four such sets of light switches, one in each configuration. However, as I just said, in quantum, the vector, the states are free to rotate, so we can prepare states which are a general superposition of all these different four states. So what quantum lets us do is we can access in parallel at the same time all these different states, and consequently have a dimension that would require otherwise an exponential resource on a classical computer. And this is how the number of classical bits, classical resources blows up as we compare it with qubits. Already around 100 qubits, just 100 qubits, we need more atoms than there are on planet Earth. So it becomes completely impossible. So with that, turning towards the algorithm side, so there's two terms, which aren't very different, but I'm still going to introduce them. Quantum advantage, which is a weaker claim, and quantum supremacy. When a quantum computer can perform some computation that is faster than even the best classical computer out there, then we say that we have quantum advantage. Whereas for quantum supremacy, when we can compute a solution to a problem which no classical computer feasibly can, then we say that we have quantum supremacy. And why I say this is because of this following Venn diagram. So there are easy problems on our classical computers, like adding, multiplying, etc., which take polynomial or better time on our devices with the length of the problem. But then there are classically hard problems, which take an exponential time or super polynomial time to do. And these are classically hard. An example would be factoring prime numbers. Given a number, what are its prime components? And that assumption that it's classically hard is the basis of modern day encryption in our devices. But what's interesting is that from computational complexity, there are several problems that are quantum easy. So they take polynomial or better time on a programmable quantum computer, but they're classically hard. So this opens up a vast avenue for doing applications in quantum chemistry, material science, machine learning, and optimization. And what I'm going to talk about is just an example of a quantum algorithm now, which provides us with an exponential advantage. So I'm going to talk about supervised quantum clustering. This work was done by Seth Lloyd from MIT. And the basis of this work is that machine learning tasks often require very large training sets, large number of feature vectors, so big data living in very high dimensional vector spaces. Well, quantum is naturally suited for this because it can handle high dimensional vector spaces in very large tensor product spaces. So why not encode these tasks in quantum and do the manipulations in quantum as well? Remember the block sphere? If I basically, that belongs to C2. If I stack up n qubits, then the Hilbert space, the dimension of the vector space, blows up exponentially. And put it another way, if I have a very big vector, 2 to the n dimensional, to encode it quantum mechanically, I would just require n qubits. So what's happening is that with a device that can encode this, we can do this, which is a QRAM or a quantum random access memory, we can exponentially compress the classical data into a quantum system. And I'm just going to briefly glance over this algorithm. It is the k-means clustering algorithm. So what it does is that we have, let's say, a bunch of points, and the bunch of points are arranged into different sets, let's say 2 or 3 sets. And if you're given a point, which is a vector in a space, and we are basically asked to assign that point to one of these sets. So what we do is that we just evaluate the distance of that point from the centers of the different states and just assign the vector u to the state with the smallest mean distance. And that's it. The long story short, this takes an order which is polynomial in m times n, whereas the quantum version, you can do it in logarithmic of mn. So it provides you an exponential speed up. And what the quantum version does is that first of all, you encode vectors as quantum states. Then you introduce an environment variable, the ancilla, and you construct a very carefully constructed case psi. And then you, basically in any quantum algorithm, you have to massage the state that you begin with to arrive at a state which has some useful information, so that if you make a measurement on that wave function, you get probability amplitudes that give you some information. So for instance, here, from psi, you perform a swap test, you arrive at another state, you arrive at some state, and you basically want to figure out what is the probability that that state is actually phi. So the distance that we are after, which I introduced here, is basically a factor times the probability that you actually measure phi. And that's it, we are done. And not just this specific distance finding, but if you're dealing with other linear algebra manipulations, like taking the inverse of a sparse matrix or doing other kinds of operations, all of these computations are exponentially faster on a quantum computer. So that's the advantage. And with that, and there are more algorithms for learning, but I don't have time to go over all those. So there's a classifier network, which basically kind of like classifies between images, and it actually has a higher accuracy uh, compared to a classical device, classical network. You have the quantum approximation optimization algorithm, and you have unsupervised quantum learning, where you don't explicitly give the labels, and it's quite similar to what we talked about. So with that, I'm coming to the concluding remarks of the talk. So first of all, I think that theoretical frameworks from physics can provide insights into deep learning problems. And one way to tackle interesting advances for deep learning is to probe the relevant physics involved. So whenever we are trying to make advances in deep learning and we are stuck, what's the corresponding physics say about it? What insights could we derive from physics? That could be an interesting approach. Studying parallels between statistical physics and learning could be an interesting step towards common sense deep learning with generalization and confidence capabilities. And finally, with quantum hardware and these algorithms will get more prominent in the age of big data. And to make the most out of AI and deep learning, we need to quantize algorithms. And finally, I would highly suggest physicists, undergrads who are in the audience and they're studying, to consider deep learning as a career path. And with that, these are the references and links that I've used throughout the talk. And thank you all for being there on the webinar. And if you want to connect with me, this is my LinkedIn handle. And I promise to give a superposition of good and bad answers. That's my poor physics joke in this talk. Thank you, everyone.
Thank you, Jana. Will you take a few questions from the audience, please? Will you take up one or two questions from the audience?
Yeah.
Hello, sir. My name is Raju. So I want to know how to calculate quantum volume of a quantum computer.
Could you repeat the question, sorry?
So quantum volume, based on quantum value parameter, we will say this is greater, this is okay, quite it has to work on. So that is what I want to know. So some D waves, they will construct quantum computer with higher supremacy. And so that is what quantum volume will be the parameter to I would say this is higher, this is lower in quality.
Right. So I think what they try to I don't know the exact formula, but I think what they try to do is basically first measure different parameters like quantum fidelity and quantum coherence. So if I say prepare the qubits in a particular state, what is the time? What is the time scale to which the qubits are basically maintaining that coherence? Because the very essence of having a quantum computer that can work is not just to prepare the state, but basically have this this coherent superposition long enough so that I can run the algorithm that I want to and get the final superposition so that when I make the measurement, I get the answers which encode that information. So first of all, the qubits or the system, whatever qubits we are using, they need to be coherent. And then there's another parameter which is like if I'm making different operations on the state by applying different gates, what is the fidelity of my operations? So those are two parameters that are definitely very important, but I'm not sure what parameter you're referring to.
So one is decoherence. That decoherence should be lower. The another one, can you please repeat it, sir?
And fidelity, the quantum fidelity.
Fidelity. Yeah. Okay. So number of qubits, that will not come into the. We will not consider that number of qubits.
So I would think that the number of qubits would be involved because if you have between operations where you're basically say applying a single gate to one qubit, that is pretty easy. But if you're applying a quantum gate to say two qubits, like a control gate, that would have a higher error. So the number of qubits would matter, because it was easier, say, for Google and those companies to have to show quantum coherence for just a few qubits. But just last year, they made some claims with the Sycamore processor that they have gone up to 53. So the number of qubits definitely comes into the picture.
Thank you, sir. Thank you.
And also, like, one more thing, like, pretty basic, you probably know this, but when we are talking about qubits, most of the time we're not talking about the actual, we're talking about 53 logical qubits. So to actually have these qubits in most systems, you have a way higher number of physical qubits. So the logical qubits is actually encoding the information, but because the system is very fragile, you're basically having a whole lot of physical qubits, maybe in the order of 1,000 qubits, in your actual device, in your actual system. So that's why it gets very tricky.
Thank you, sir. But I have another doubt. I do not know whether it will fit in this flow of your explanation in quantum computing. So I want to know, if we entangle 3 qubits, then how will it work?
Okay, so there's a maximum limit to entropy, entanglement that can be shared. So if I have a bell pair,
I mean, theoretically.
theoretically, yes. So if I have just two qubits, right, and I prepare them in a bell state, then they're already maximally entangled. So you can't, if you add in another qubit, you can't create any new entanglement without destroying entanglement. This is basically the monogamy of entanglement, where if you have two particles which are maximally entangled, you can't bring in a third into the picture. What you can do is that you can prepare a 3-particle state, like a GHZ state, which is again maximally entangled. So you would have to basically prepare the state where the states are sharing entanglement, but no two particles are then sharing maximal entanglement. So the entangled resource gets distributed between the particles.
Thank you, sir. Thank you. I think I need to understand it more.
Thank
So
you.
I will work on it. Thank you.
Anita Dalai, are you there? You can go for your question. Anita Dalai. Okay, I have questions for her. What is the difference between statistical artificial intelligence and classical artificial intelligence? Question from Anita.
Okay. So there's a framework called Bayesian deep learning, which is basically statistical machine learning. And as I very briefly kind of hinted at, is that with Bayesian machine learning, what they're trying to do is instead of arriving at single values in our optimal solutions, we instead deal with probabilities, and probabilities forms the basis of statistics. So instead of just getting an answer to a problem, we want to know what distribution do the answers belong to. So in traditional machine learning, as it came up, you did not have this entire notion of probability distributions as the solutions to your parameters. But with statistical machine learning, you have error bars. You arrive at confidence parameters. That this is my prediction, and I am confident about my prediction to this extent. So I would say that statistical machine learning is kind of a bigger framework that does encompass classical machine learning. It's a bigger generalization.
Okay. Question. What is the scope of artificial intelligence for Indian students in abroad countries?
In abroad countries. So I think this is a very good question. It's a very important question, because what we see, the trend around the world, is that if you're looking at, say, I mean, there are different metrics to answer this question, but if you're just looking at papers that are being published online, then it's basically, I think, the United States, China, maybe Germany, and the UK, that is like very leading the entire trend. So as Indian students, I think it's very important that we take up this very seriously, because I think this revolution that is coming, this artificial intelligence revolution that is coming, while it is really awesome, it is really cool, the sort of things that we can do with this technology. At the same time, it is also very dangerous because it can lead to huge inequalities. So I would really encourage and urge the students who are still in college now to pursue this, and not just think about doing it abroad, but bring things back to Indian institutions. There are several really good institutions that are pursuing this research. So I would really encourage them to first consider India as uh, as a place where they can start their journey.
Okay, thank you, Deva. Any other participants? Do you want to ask any questions?
Hello, sir. Hello, sir. My name is Nikhil. And I just wanted to ask that how do you choose the optimum learning rate for supervised learning, like classification problems and sort of?
Right. So it's a very technical question. So I heard it. So the question was that how would you choose the learning rate for, say, supervised learning example? So it is referred to, the learning rate is referred to what's called a hyperparameter, because basically the learning is going on in a loop, right? And the loop is controlled by this learning rate. Well, if the learning rate is very big, then you're just going to miss out on the solution. You're just going to get knocked around. So think of the learning rate as kind of proportional to the. I mean, it is proportional to the length of the vector we had here. Sorry, it's going to go back a bit. Yeah. So think of the learning rate as being proportional to the length of the vector here, right? So if you make the length of the vector very big, right, you're just going to miss this valley and you're going to get knocked around, and you won't really end up anywhere. You're just going to knock around. You would define like you would get knocked around a ball, which is the size of your, I guess, learning rate, something like that. So you don't want to choose a very big learning rate. You don't want to choose a very small learning rate because it would take a lot of time, and you don't want to do that. So it's a hyperparameter, and for most problems, like say you're just starting from scratch, building a model for classifying images, you just that's something that's reasonable, like maybe 10 to the minus 2 or something on that order. And then you see what happens. Like within, say, by training it, say, for 500, maybe 1,000 episodes or more than that, what do you arrive at? What kind of what kind of validation accuracy you arrive at? And then you try to change it. So obviously you could change it as outer loop, but that is very inefficient. So you usually try with something that is reasonable, and then you kind of play around with it.
Also, there is a trade-off between precision and recall, right? Whenever we
Sorry?
are trying to, there is a trade-off between precision and recall, basically, right?
Yeah, yeah. Because you don't want to be fitting your data very like too much. So you need to add in very many parameters that go under regularization, so that you go for the sweet spot. Yeah.
Thank you so much. Thank you so much.
Thank you. Any more questions? All right. Dev, it was an excellent presentation. I hope our participants really benefit from your presentation. You are very young and dynamic, a very bright future in the coming days. On behalf of Saint Aloysius College, management, principal, and all the participants, and especially from the Department of Physics, I would like to express sincere thanks. Once again,
Thank you.
hope once pandemic is over, we'll see in India of course, in Bangalore.
Yeah, thank you, sir.
With that, I would like to conclude the meeting. Thank you all the participants for your wonderful participation and cooperation. Once again, thank you, speaker. Thank you.
Thank you for having me. Thank you.
The link is not working.